Hello, everyone. So this is going to be the third one, and there will be another lecture on the general form of linear quadratic. This is still a particular case. So yesterday we have seen the Nash equilibrium concept, and this lecture will go beyond. So we'll introduce social cost. We'll see Nash bargaining. That's for cooperative meaningful type games. We do bargaining instead of fighting with each other. We are going to sit down and negotiate and talk to each other. And there will be other notions related to altruism, means you are helping the other. These are things that we observe in reality. So we try to incorporate those concepts, in particular something related to experimental game theory and psychological game theory. So the other topic I will discuss will be on robustness. So that's related to zero-sum games or what type of payoff you can guarantee. Okay. And finally, we'll discuss something about competition. Competition is when you put competition and cooperation together. And that's my favorite topic. Because in many examples, you see that actually there are some part where these companies are maybe competing, but there are other part where they are really cooperating. They need to survive, they need to share some resources. It's happened for infrastructure type of building, where they need to cooperate in order to get the market, and then they start sharing the market. So there will be competition and cooperation at the same time. So that's what we call co-opetition. And we'll try to see how we can incorporate this idea in meaningful type games. So the agenda is to start with the full cooperation of the model of yesterday, where we include a common noise. I didn't write down the PDE, but today or tomorrow you'll see the infinite dimensional PDE associated to it. And then we'll go to the Nash bargaining case. The Nash bargaining, where we try to find a Nash bargaining solution instead of the Nash equilibrium solution. And this is interesting as a cooperative solution concept. And then, so I would like to mention that Nash has done the cooperative game theory as well as the non-cooperative game theory. And in the game theory literature, the non-cooperative is more popular. I don't know why. But the cooperative part is as important as the non-cooperative version, because we use non-cooperative games to explain that we need to cooperate. That's why it's much bigger in that. But all this is to explain that they need to cooperate. And in order to show that they need to cooperate, you need to show that they are better off by, and for that you need to compute a non-cooperative solution, right, to compare. And then we'll go to the robustness and zero-sum meaningful type games, where we have conditions that are similar to the Isaac's conditions, so the min-max and the max-min. The min-max is always greater than the max-min, but there will be equality in some cases. And this is related to what we do in optimization, where the duality gap, we know that if you have the dual problem and then the primal problem, you get the upper bound for the primal problem as a dual problem, and vice versa, a lower bound. Now, there will be no duality gap condition is related to what we use in differential games as the Isaac's condition for having a value. And then the last part, and then the next step will be on other regarding payoffs. So this is a game situation where you consider not only your own payoff, but also the payoff of your friends, the people you care of. Right? This is something that you could use for families, for example. It's not about yourself only, but some group of people you care of. Okay, so that's called other regarding payoffs. It includes some of you might be empathetic here, so empathic payoff. Some others concept like, okay, you care about others, but in a negative way. So that could be like you are trying to destroy somebody else, whatever. And then there are people who destroy themselves. So this is observed in particular diseases that people might have, where they try to kill themselves. You have probably observed in specific secret of spittles and so on. So those can be captured through some parameters, and we try to do that. And then I will include switching regimes where, so we have one dynamical system and then another one, and you jump from this dynamical system to the next one with some external Markovian switching. That's completely independent and external thing that happens. Okay, that's this Minfield type games with jump diffusion and switching regimes. I try to build up to be close to the original model I presented you in the first lecture. So this is the agenda. So let's start from what we have seen yesterday. In the game context, we have a loss function that is quadratic in the state, quadratic in the mean of the state, quadratic in the control, and quadratic in the mean of the control. And we have been minimizing this type of loss function with expected value. So the global optimization cost, or the social cost, is when you sum all the costs of all the agents. And then you take the expected value. Now, this decision is made jointly. All the agents together, they optimize this function. So it means we are a team now, and as a team, we are going to make that decision jointly. Okay? So that's back to standard optimization problem, except that you have the expected value of the control and expected value of the state there, conditional expected value. So if you have the hat, it means the conditional expected value. It's a random variable. Okay? Condition on the common noise. Right? So that's our state dynamics. So here, sigma and mu are just function of time. There is no state and control for the moment. So that will happen in the next lecture. The initial state is independent on the Brownian motion that is here, and the Poisson jump process, and here. Okay? So we want to solve this problem. Again, the strategy is the same. We have a guess functional for the optimal value here. That will be quadratic. Why quadratic? Because the state here is linear. If you put a linear control, then by taking the quadratic term, everything stays quadratic. So you start with the quadratic functional as an answer. You apply Ito's formula with the common noise on it, and then you derive the explicit form for the coefficients. Okay? Excuse me? Li is the quadratic cost functional. I will write down here. So Li is a certain coefficient, and then you have the state, the terminal state. So this is at the terminal state square. So state square terminal plus Qi, another Qi, S bar, S hat terminal. Okay. Plus, so the running cost will be integration from 0 to t. And then here you have a Qi of time t, S of time t square, plus Qi bar of time t, S hat time t square, plus a coefficient here, another coefficient, Ri, the control input square, plus control Ri bar Ui hat square. Okay? So quadratic in the control, quadratic in the mean of the control. And these hats are, so S hat is the conditional expectation of S given the filtration generated by the Brownian motion up to t. That will be S of time. Okay? Same model as yesterday. So you want to minimize the expected value of this function. So you can write down this as a conditional variance because you have the conditional mean here. Put them together, get conditional variance. So that's the relation with variance reduction problem. Okay. So we start an answer that is similar to this with a linear term on it, and we are going to identify the coefficients. Question? No. Okay. So So when you start with this unset, so a coefficient here, alpha naught, we do not need all the alpha i's this time because we have only one objective functional, so one coefficient, alpha naught here, beta naught, gamma naught, and delta naught. Those will be function of time, but also they are going to be stochastic this time because of the common noise. Okay? And we want to identify those coefficients. Okay? So we write the functional in this form, and then apply Ito's formula to this functional, and then derive the SDEs associated to the coefficients. Okay? So the optimal cost will be this one, the expression here. The optimal control will be linear state feedback, but there is a conditional expectation of the state with respect to the common noise on it. Okay? So your state is your optimal control depends on the state, but also on the conditional expectation of the state. That's important. And the conditional expectation of the state can be obtained this way. The common noise is observed by everyone. Okay? It's something external that happens and everyone sees that. So this is known, this is observed, and the rest of the things that are inside, so this is the state itself, the conditional state itself, and this gamma is solved in another equation that we said. So this part will be computed offline, right? So this is given by the dynamical system itself, and this will be known. So this S hat is something that you could compute independently of the other part of the thing. So in function of the parameter only, typically, right? So you compute this thing, you plug it there, and it's stochastic just because of the common noise. And then you are supposed to observe your state. That's called state feedback solution. If you don't see the state, you cannot employ this control. Then it's better to go to open loop strategy, where you just have to pick a function of time and not as a function of state. So in the context of games, the feedback solutions are in general different than the open loop solutions. Those are only function of time. You are not allowed to use the state because you don't know it. Here we are assuming that it's perfect state observation, means you see the state and you estimate your S hat and plug it there. Okay? So this is perfect state feedback global solution. So the coefficients alpha naught solve the Riccati equation. Again, this Riccati equation has a unique positive solution subject to Q naught here to be positive and Ri to be positive. Okay? So last time we have seen an explicit example of the solution for it, alpha dot minus alpha square equal to 0. The terminal value at time t was Q. Remember that. The solution was alpha at time t to be 1 over Q plus t minus tau, something like that. So if Q is positive, if Q is negative, there is a blow up at this time before there is a blow up in time. But if Q is positive, then there is no blow up between 0 and t, and you are happy. Okay, so that's the positivity condition. Q has to be positive if you don't want to have a blow up in finite time. Okay? And positivity condition here, in this context, it's almost nothing, because we are just asking this thing to be positive. We are minimizing S squared and asking the coefficient here to be positive. So it's not really a restriction on it, because negative here means your loss is going to be minus infinite. Okay? So this Riccati equation is something that we really understand, and the positivity condition is not restrictive because we are minimizing the loss function. Okay. So we have a closed form solution for this, subject to the resolution of this system. This is the alpha's equation, and then here you have the beta's equation, and then gamma and delta and so on. So those are stochastic ODEs. This is because we are looking at stochastic common noise problems. If you remove the common noise, you are back to the classical mini field game without common noise, and you'll have ODEs instead of SDs. So this situation where you optimize globally is called the fully cooperative approach. So it's global optimization. It's reduced to a simpler recovery because you don't have systems between agents. There is only one alpha node. There is only one beta node, and there is one gamma, and so on. That's much simpler than the game situation. And the common noise regularizes somehow. Even if there is a blow up, if the common noise coefficient is non-zero, it's kind of regularization. There is a kernel. So that could be useful. Fine. It's S hat is adapted process. You have seen it. There is only B not there. So this is adapted to the filtration generated by the common noise. And I have already explained that it becomes more regular. So the advantage of the common noise here is that if you have solutions that blows up in finite time, but with the common noise, you get more regular solutions. That's the only advantage of it. Well, it depends how you say it, but it's a positive thing to have a common noise here. Now, let's go to the bargaining situation. So some of you might not be familiar with what we call bargaining, Nash bargaining. So here is the situation. We are not going to fight with each other. It's time to sit down and discuss. It's time to sit down and start negotiating. So we want to negotiate and find a point where we are all better off, all the participants to the negotiation. In practice, it's more involved because there are a lot of offers and offers back and so on, re-offer, and it goes overrun. But the static formulation of this is to maximize. So the loss function here I'm putting is the loss function we found yesterday, the Nash equilibrium, the loss function of I at the Nash equilibrium of yesterday's system. And V is the set of all the costs that could be achieved when they work together. It has several components, V1, V2, and Vn. There are n agents, and Vi is the loss that will be going to agent I. Now, we are going to maximize this all together because we are sitting down together and negotiating. You optimize this, the loss that you get is going to be the Nash bargaining solution. Okay. For two players, it means that you just optimize the product. You just minimize the product between L1 and L2. I dropped this part. Okay. Just minimize the product altogether, U1 and U2. Minimize that product instead of minimizing separately. Okay. If you minimize this object, then the solution that you get is the negotiation solution. Of course, in practice, people have different negotiation power. Okay? If you are much more stronger than me and you are much more powerful, then what you are going to do here is you put your power here. Okay? Alpha 1 and alpha 2, those are positive numbers. So these are weights associated to each person. So this is your negotiation power. This is my negotiation power. And the solution will be better than the Nash equilibrium, of course. Right. So we consider this problem. You see, there is already an issue because my previous problem was strictly convex in U, but now, since I'm considering the product, it's not convex anymore. So I have a problem. But look at the set of costs that you could achieve. So even if this problem is not convex, but this set is convex, then you could map the product optimization into weighted optimization. It's very well known problem for Pareto optimality. So you just optimize this weighted sum. Okay? You need to find the proper weight to match with the weights you obtain here by just differentiating. So this is what we are going to do. The optimal weight to get the solution to this problem is written here. It's just basic differentiation. And then solve this problem. But this problem is the one that we solved in the previous slide, with just some different weights. Right? So that's how we solve the Nash bargaining problem. And then The type of curve you get is the following. So this is the set of achievable cost. The set of achievable cost. So player 1 is this way, and player 2 is here. Something like that, convex set. And we want to find a cost that is here in the Pareto frontier. Okay? So that will be the cost of one, the Nash bargaining solution. Nash bargaining, whatever, solution. Somewhere in the Pareto frontier. So we are trying to find this cost instead of some cost that is here, that is the Nash equilibrium cost. Okay? The Nash equilibrium cost is much higher for everyone. Okay? So it's important to look at the Nash bargaining solution for this type of reason, in particular in the quadratic problem here. So with the Nash bargaining solution, the cost of both players gets reduced. Okay? So that's one of the conditions for the negotiation, actually. If I want to go from this solution to this solution, player 2 will not be happy if I propose a cost that is higher. If I say that the point of negotiation is here, 2 will not be happy. So it will come to the negotiation only when the cost will be lower for it. So that means that you should look at from this curve here. And same for player 1. It can go to the negotiation only when the cost is in this area. Okay? And the minimum so this is all the achievable region of the cost, and this symmetric solution is when the negotiation power are the same. So then we got the symmetric Nash bargaining solution. If the negotiation power are different, like alpha 1 and alpha 2, then you get somewhere here or somewhere there, depending on the side you go. Okay? So you get one of the Pareto optimal solution, one of them. Are the alphas the same as these weights, W? Yeah, so this is the W that matches so the W here should be this one if you want to solve this Nash bargaining problem. Alpha is something different. You could connect those two, but alpha is negotiation power. So typically you go here, you put coefficient alpha I on the top. So this one was for symmetric Nash bargaining. So the asymmetric Nash bargaining consists to put some weights here, some other weights. Means you are more powerful in the negotiation. You see some companies have more power than some others in terms of negotiation, and that gives them some advantage somehow. And that advantage is observed here. Instead of going to this point, it goes in one side or the other, depending on the negotiation power. But it always stays in the Pareto frontier here, because otherwise you could still lower the cost. So this concept is important, especially in games or especially in negotiation problems, and that's why people have. So that was proposed by John Nash in the 52 or 53, the same John Nash. Okay? So we want to do that in Minfield games, Minfield type games, and I thought this could be interesting to some of you to know about this concept and then start using them. Okay. So the careful design of the weights to match the negotiation power is important. You need to compute this by just differentiating and matching the weights there. So now, next step will be on the zero-sum case. We call it also robust optimization. Now you have two players, player 1 and player 2. Player 1 minimizes the cost. Player 2 is going to look at the worst case, means is going to maximize the cost. Okay? So 2 is like my enemy, if I am 1, is picking up a parameter there that maximizes my cost, and I am minimizing my cost. And the state dynamics is the same as before, but now with two interacting players on. Okay, I wrote the dynamics this way because if you take S minus S hat and S has separately, these are two orthogonal. It's an orthogonal decomposition. It helps when you do the conditioning later on. Okay, it doesn't change the dynamics. I just rewrite it. Okay, the cost function same. So you see now I rewrite in this form, so that this orthogonality appears. So this is like conditional variance. Okay? That's conditional variance if this is not random. Okay? So we want to solve now this problem. So this is what we call a robust problem, or zero-sum game if you could exchange the position of the env into soup. So this robust optimization problem, so we have been looking at that robust meaningful games in the context of meaningful games, but here I look at the meaningful type version of it. Okay? And if you are interested in the meaningful game version, that was published in the Dynamic Games and Application a couple of years, 2 years ago. So in the meaningful type game, you could solve this problem with now explicitly with the new coefficients, alpha, beta, gamma, and delta. This is the optimal control of player 1. This is the optimal control of player 2. Look at in the problem. So I want the one who maximizes one positive coefficient, the one who minimizes one negative coefficient. Okay? Otherwise, I'll get infinite. Right? So just the coefficients for the maximizers to be negative because you want concave on it, and the minimizer to be positive because you want convex on it, convex concave. Right? Then you get a unique solution, and these are the unique solutions. Right? So the coefficients solve Riccati equations as similar equations as before, but there are small differences. This sum was different in the previous one. The zero-sum solution is different than the global optimization solution, which is obvious. So that's something that you could see. But this time, we want this sum to be positive. Okay, so this is good. This to be positive, right? We need these coefficients to be positive. If you go back to the assumption, this is what we are assuming. This term is positive, the other term is negative. Right? So just the only assumption you need for those things is just that. Very simple. Strict concave, strict convex, you are done. And that with common noise. So when I will write the PDE for the common noise, you will realize that instead of solving these stochastic Bellman equations, you are better off to employ this technique and then go back to your PDE, plug there, and show that it satisfies. At least you have an example of explicit solutions to the master equation. Okay, so now let's move to the most interesting part of the talk, if I would say. We will consider n agents, and there will be some relationship and connectivity between those agents. That's typically over a graph. If you are connected to, let's say you are agent I, and your friends, the people to whom you are connected with, that will be your neighborhood. So this is the neighborhood of I. And any person who is part of that list, you want to decide if you consider him in your decision or not. So that's the matrix of the empathy structure. So the matrix of the relationship. To yourself, you attach a certain coefficients. Okay, that could be positive and or negative. If it's negative, it is self-destroying himself. If it's positive, well, you are partially selfish. Lambda ij. So if lambda ij is positive, you are helping j. I is helping j. If lambda ij is negative, I is malicious against j, spitefulness. If lambda ij is 0, well, you are selfish. Selfish toward j. So you focus on yourself, not on the other. Right? So it includes partial altruism when lambda ij is positive, maliciousness when lambda ij is negative, and selfishness when lambda ij is 0 and this is positive. And self-destroying when lambda I is negative. So all those combinations. So because in our society, when you look at, some people are altruistic, some others are selfish, some others are partially cooperative, and some others are malicious. It's there. Now, what is the proportion of those? What is the distribution of those? I don't know, but this is there. This is observed in practice. So that's why we try to incorporate those in the models. We try to write a paper on it. We could find on the internet some of these discussions. So I summarize the discussion here. For lambda ij negative, I call it partially spiteful. So this is same as maliciousness. Partially because the lambda ii was not discussed here. When lambda ij is 0, ii is positive, you are partially selfish. And when lambda I is positive, you are partially altruistic toward j. And for the ii, so if lambda I is 0, you are selfless, means you focus on the others. If lambda I is positive, you are partially selfish in the sense that you consider yourself, you don't completely forget yourself. If lambda I is negative, you are self-abnegating, means you are self-destroying yourself. Okay. Now we are in good business. We could write the cost function, the previous cost function I presented with the lambda i's and lambda ij's. So this is my new cost function, quadratic in the, so this is the variance term, if you want. So this is the variance term with the ii and ij. I consider all my neighborhood on it. This is the expected quadratic of the expected value term with the lambda I and lambda j. Same thing for the running cost. I put some coefficient half for my calculations to be easier. It's not really important. And the state dynamics solve the same dynamics as before. With all the agents together, these are the control actions of all the agents, and this is the mean part of all the agents. Okay. Now, can we solve this? Well, it doesn't change anything, right? Now you do the same procedure with those lambdas. And after that, you could change the lambdas. If it's positive, what happens when it's there, it blew up. If somebody was attaching a positive sign to my utility, but to the next round, immediately change his lambda. And it will be blew up. So he was helping me, and now he's trying to destroy me. It is observed in practice. You could see around, and you see that some guys were friends, and now they are not friends anymore. Okay. So the explicit solution, as I said before, so this is similar as before, but now we have those weights that appears in the optimal control, and in the Riccati equations, it is now modified with those terms here. Okay? That it's more ugly, but still it's not complicated. It's something doable. Now, this is for gamma and delta. And we have observed a couple of things that you don't see it when those lambdas are not there. So there is some kind of inconsistency in the model, in the sense that the lambda I have given you there is first order. If I apply another lambda, means second level of reasoning, or third level of reasoning, or fourth level of reasoning, is the structure of the solution going to change or not? So we say consistent if in all those reasoning, the equilibrium structure is the same. Okay? So that's the same thing for Nash equilibrium. We say, actually, I know that you are going to optimize. That's why I'm plugging that in my optimal control. But do you know that? You should know, because if you don't know, you are not going to use that strategy. Right? So I know that you know, and you know that I know, and I know that you know that I know that you know, and so on ad infinitum. So this is what we call common knowledge of rationality. And that's how the notion of rationality is built. So this is the first order version, and I want to know if it's consistent when I go over this reasoning. Now, it turns out that for Ampati structure, it's not consistent. In particular, for pure altruism. Pure altruism means I am helping the other unconditionally, and I don't attach any weight to mine. Did you observe any of this behavior in nature? Pure altruism. A grandmom helping with small kids or something, whatever. Pure altruism. So I am optimizing your objective without considering mine at all. That's what we call pure altruism. And we want to see if that exists in nature. That's one thing. The other thing is mathematically, it means the alpha ij, lambda ij is strictly positive, but lambda I is 0. Now you do second order reasoning. You take the square of that matrix. You see that it's not consistent. Okay? The equilibrium structure is going to change. Because there are matrices where the square brings you some positive component to himself, right? That type of thing. So that might not be consistent, and pure altruism in particular is inconsistent. It can be consistent only in the trivial case when all the lambdas are zeros. It means the loss function is 0. You help or not, it doesn't change. Okay? That in that case is consistent, but that's almost the only case, or constant loss function, this type of extreme cases. So if you do partial altruism, there is a gap, there is a reduction in the inequality gap. So some of you, if you are working in social norm problems, you might be interested in it. You could reduce the inequality gap by designing this lambda to be partial altruism, means they are positive. Okay? So the gap between the equilibrium cost of player I and player J, the difference of that, in absolute value is reduced, which is interesting. It means that we need to be more social, more partially altruistic in our society if we want to reduce inequality. But are we interested in reducing inequality? That's the other thing. Despite means that when lambda ij is negative, you might get things that are not admissible. Of course, there is a blow up in finite time. You integrate to get infinite. It's not admissible, right? And well, if it's not admissible, you don't have existence of admissible equilibria, obviously. So you get in this simple thing, you get non-existence of equilibria by just playing with parameters. Okay. So inconsistency means I play the lambda again. I apply the same lambda, second order lambda. So what you have is this. The first order lambda is just a matrix here, lambda times L, right? L is a vector, lambda is a matrix. This is the first order. So second order will be lambda 2 here. The kth order will be a lambda k here. That matrix to the power k times L. You play that game. Okay, this is a vector. Each person has the component there. You play that game. You want the equilibrium of that game to be the same as the equilibrium when k is 1. So at any order in the reasoning, the equilibrium structure remains unchanged. This is not true, obviously, for pure altruism. Okay. So that's one thing. Pure altruism is inconsistent. That's from the math. But in practice, we have so far never observed pure altruism. A lot of people are working on it in nature, see if there are some animals that are helping some others, is there any benefit for them, and so on. But so far, we have never observed any pure altruism in nature. We see partial altruism. So typically, you are helping somebody on the street. Now, what's your benefit in doing that? And we always find something that says that, okay, maybe that's for my reputation, what people will look for me, whatever. We always find something that justifies why you are doing that. It's a service to the nation, whatever, you get some medals, I don't know. But there is something we found always. There is a reason on doing that, so far. So if you are able to find that, we'll be really happy, because people have been looking for more than 50 years that pure altruism in nature. That's for yourself. Okay, so now let's go to the regime switching case. I take the same model, and now I include switching. Switching, remember, switching means you start with one dynamical system. So this is your dynamical system, one model, and here is another model. Okay. Now you want to switch. You want to jump from this model to this. Well, let me write different ones. Okay, this is another model. Okay, so you want to. They are all linear. Okay, with some noise. So you want to switch from this version of the model to another version of the model. And there will be a Markov jump. So this is state 1, this is state 0. And you go from 0 to 1 with some rates, Q01, well, 1, 0. And you go back here with Q tint 01. And the rate to stay is, the total sum should be 0. So this is this parameterized interface. So, and this Markov jump, Markov switching regime is independent on the other processes that are in the system, the Brown motion, the common noise, and so on. Okay? So you switch from one dynamical system to another dynamic system and back one day. Okay. So that's regime switching. And it happens when you have situations where we have several seasons, or I don't know, you try to find your favorite example. You switch from one season to another, or one regime to another, whatever. So the system will be modified this way. The loss function is same as before, but now the dynamical system, to say that they are different, I put coefficients that depends on the regime. So S tint is now the switching regime. It has finite number of states. Okay. I'm going to write down ODEs, and if you have ODEs with infinite number of ODEs system, I don't want that. So finite number of states, and the coefficients now depends on time and switching regimes. Same for all the coefficients, including the jump process coefficients. Okay? That's the only modification. We know that if we have this pure jump, you can write down in a martingale form, and the M tint is coming from that, the martingale formulation of the S tint. Okay? That martingale will be useful when we apply the Ito's formula. Okay? So this is the new problem to solve. We'll see that actually you will have a new version of the Ito's formula. And that's it. And then apply Ito's formula, the new Ito's formula. And I have given the Ito's formula in the first lecture. And then your solutions now is much smaller, but the only differences are the switching terms that will be added to, and you could read in the slides. It's something doable, okay? And you could do switching for global optimization as well. That's maybe easier to write down, and we'll see what will be for the global optimization. You get these switching terms. So you have less number of equations. Okay. So there will be a linear term in the alpha naught. Alpha depends on the switching. That will be added to that with the jump rate, the switching rates. So from S tint to K, and you are summing on all the Ks different than S tint. So this linear in alpha naught term will appear. Q tint is fixed. I mean that parameter. These are fixed. So this does not complicate if you want to show that there is alpha naught that is positive, because this term is linear in alpha naught. To show that this is positive. Before, with that term, I was able to show that there is a positive solution, right? When those terms, coefficients are positive. Now, when I add this term, I need to show that there is a positive solution almost surely. Because that term is linear, you just integrate it, and you get immediately from the integration formula. That is positive. So we are happy. This is positive solution, and we plug it back in the previous formula, and we get our explicit solution. Because when there is a positive alpha, everything is done. There is no other issue. Okay. So if you want to write down the PDE associated to it, this is what we'll do in details. The PDE associated to it brings integral terms because of the jump and summation term because of the switching. And if for those who want to do numerics, when you have integral, so you need numerics specialized to the integral term because you need many other states to include. So the more points are involved on your grid, the worse will be your scheme, because you don't know those points. So you just start with the guess functional and put there, right? When I do my backward forward or your other favorite scheme, at some point, the solution I started with, the guess functional, is not the solution. So I plug there V of, so this is the term that will happen. The value at a state plus mu minus the value at the state minus mu, the derivative of the state. This is the term that you need to integrate up over the measure. And you need a numerical scheme that discretizes this thing. But the value is what you are looking for. So if you are at S, you don't know the value at any other points that are there. So that creates extra difficulty in the numerics. Well, there are a lot of numerical schemes for integration formula, but those are just approximations, right? So you need to find your favorite thing there and plug there. So we believe that if you have approximate solution from the linear quadratic, it gives you a reference curve to start with. And when you plot your numerics and you see some wrong things, maybe the linear quadratic could give you a reference trajectory to start with. It's not solving the problem. It's just to say, I want to check if my numerics are doing right or wrong. Right? In that sense, it could be useful. It's not a complete statement, but you need to check those things because it always plots a curve. What you do, it plots something. How do you know if that's proper, is going to the right or wrong direction? If you have any solution, I'll be happy to take it. But especially if it's not quadratic, because when it's quadratic, we know how to do it. Okay? So the recitation will be on application of this to blockchains. I thought that you might be interested on this emerging markets and people who are excited in investment. We do with meaningful type games to regulate the markets. It's on the regulation part, and Wu Chen will discuss about it. So, any question, comments? So if you have a switching, if you have a continuous time Markov process with finite states, you take the indicator associated to it, and you can write the jump from state I to j, the number of jumps. You could write as a sum of the first term plus the martingale, which is just the difference, that make it finite. Zero expectation, right? So the martingale representation of your continuous time Markov chain. So you can write your process as a first term plus a martingale, and that is useful because when you do Ito calculus, you want the martingale to appear, right? So this is just rewriting the process itself. And I am adding this. K can be 0. If you don't like it, just put K here to 0, and that term doesn't appear. But still, this S tint appears in the coefficient. Right. So we have done cases where here K is 0, but the S tint appears, and that gives you different equation as well. So if you go back to the solutions, it's difficult to see, but when K is 0, this term here, you see kappa square appears here, and when kappa is 0, this term disappears. So you get different solution. Right. But this term still appears because there is no kappa here. That's for the switching term, and this is coming from the rate associated to the martingale, the kappa. So it plays a role in terms of the martingale part, the coefficient in the martingale part plays a role in the solution. But if that is 0, you are back to a simpler one. Right. So sometimes we want to say that actually when it switches with a certain jump. That's what the last part, that kappa does. Okay. Yeah, please. So you mean I condition on the switching. So the switching process, you condition on it. So I didn't mention, but switching can be seen as also a global, as a common noise. So here, so you could do that way. So you condition on the switching. You observe which regime you are and solve the ODE in that regime. But the ODE of regime K depends on the ODE of the other regimes. The ODEs are coupled. You solve that offline. It's not part of the thing, just offline, because these are given by the parameter of the problem. Solve them offline. Of course, with the new observations you have, the new observation. I am in this state. I take this alpha of that specific regime. If I change the state, I get another alpha. You see, so alpha k, so with different regime. But those ODEs are supposed to solve offline because we know the parameters. I just need to be adapted to the other common noise. But so let's say you consider the same thing without the B naught, but with the switching. Now switching is your new common noise. Okay, I know which regime I am. I observe it. Everyone observe that. That's a common noise. And for that, I now need to go and solve this ODE offline, completely offline. And I plug alpha k if you are in regime K, alpha s if you are in regime S, and so on. Right? So you could do that. For the numerics, it will be like piecewise, it's blockwise thing, but the system should be solved offline, which are interdependent. The solution is the same. I'm solving this system, this exact coupled system offline, and I apply the rule in the condition. So the solution will be conditioned on that state, right? When you condition, you get alpha I at that regime that you are observing. The optimal control is that way because it's written here. It depends on the regime you are. It doesn't depend on the other regime where you are not. Right? So you could do that for at least for this setup. Of course, for other problems where you have correlation, if you have a correlation between the switching process and the state, what I'm saying is completely, probably it's not going to happen, right? So this switching is uncorrelated. It's independent process. Like our common noise is totally independent thing that is entering the system. It's the same stuff. Yes, please. Right. If you don't want to switch randomly, you can put, okay, at a specific time window, there will be a switch, and in between, no switch is allowed. You can have piecewise jump process. That will be more interesting because we don't want our system to switch all the time. Yeah.
For this example or another one, actually not quadratic with switching and jump and everything. Basically, just the idea about how to find this formula. So the UI star basically has always the same structure somehow.
Right.
So you start with some ansatz which has always the same structure.
Yes.
But then the equation is there will involve some additional.
Right. So tomorrow we'll see the general form when the diffusion depends on the control, the state, the expected value, and so on. Same thing for the jump process and the switching. And you'll have structure similar like this. The ansatz will change because here you have only the variance and the expected value square. You will have covariance term. We couldn't avoid the covariance there. So covariance will be added to, and some other linear with the non-adapted part as well. So that will be the general form, but it will not be a Riccati anymore because the diffusion will be controlled and state dependent. So you don't get a Riccati, but you still get an ODE, another ODE. So if you look at my lecture last year, that was non-quadratic, and you have those ODEs in that lecture. So we solved the PDE for nonlinear setup. That was last year. So, but because last year was a workshop, it was not the summer school. Okay. The nonlinear version is the video is online. You could check that, and existence of positive solution to those ODEs in the slides there as well, with the jump term and switching term. So the proper PDEs are in the slides of last year. with the nonlinear setup, the non-quadratic setup. Okay. Any other comments?